Okay.
Thank you, everybody. Sorry for the inconveniences. Yeah, we have some technical issues, but it seems that we solved them. And so today we have Medea giving the seminar. She's a PhD student in the group of physical
biological interactions in the ocean.
As far as I know, she works with the motility of very small organisms. I think that she's going to explain it better. So, thank you, Medea.
Okay. So, thank you for being here. So, yeah, I was already presented. So, today I'm going to talk about the role that certain chemical compounds play in shaping plankton predation. And I will start by saying that this work is a joint collaboration that we have with the ICM in Barcelona that we started 1 year ago. So all the experiments that I'm presenting were done by Carol Puel, who's a PhD student at the ICM, and she's in the group of marine biochemistry with Rafael Simo. So I wanted to start with a question, which is, how does predation work at the microscale? So we all have an intuitive idea of how does predation look like at our scale. But we have to think about that the organisms that we work on are much smaller than us, are like 5 orders of magnitude smaller than us, or a sea lion or a penguin. So also the tools that they will have to interpret reality will be very different from those of complex organisms. We talk about in general as unicellular organisms, which are very simple, but still will have to interpret reality. So meaning they have to know where they are in the water column, they have to know where they go, and where to find food or where to find a reproductive partner. So what you see here is a dinoflagellate, well, 3 dinoflagellates feeding on another poor dinoflagellate species. And we are talking about organisms in the order of the 10 microns. And so the question here is, how can a micropredator detect and swim towards its food? We have to think that they don't have eyes and senses as the complex organisms do. So, in general, the water column is a very patchy environment of nutrients for microorganisms. So it will be big seas of nothing, and then somewhere, some hotspots where the microorganisms can find a lot of nutrients. But even in the hotspot, it has been called like a soup of chemicals in the paper from which this picture is taken. And it was shown that even in a soup of chemical, a microorganism is able to swim and orient itself to find its favorite food. And so how do I orient the chemical soup? I already said it a bit. So it's a chemoresponse. So the process by which a chemical stimulus is converted in a behavioral response. And here in this presentation, I talk only about chemoresponses because that's what the work is about. But it's not the only way that microorganisms have to orient themselves and know where they are and where to go. It's a crazy world of possibilities, but we are talking about just maybe the most intuitive one, which is there's a chemical stimulus, and I'm able with my chemoreceptor to sense it and react to it. So when we talk about chemoresponses, we can have chemotaxis, which is the ability to sense and direct movements in response to chemical gradients. So what you see here is probably a bacteria, and it's swimming in a chemical gradient of a yellow substance. And also here it's not so easy to understand, no? Because like, okay, let's say that a bacteria swim with a run and tumble behavior. So the presence of the chemical will change the distribution of the run times and the tumbles, so that overall its average movement is in the direction of the chemical gradient. Or we can talk about chemokinesis, where the local concentration of a chemical compound is changing the swimming speed of the organism. So for example, the bacteria will swim faster if it detects a higher concentration of a certain compound, and it's positive chemokinesis and negative if it's the contrary. So in this work, we work with a very specific set of chemical compounds, which are the DMSCs. To me, this is a family of compounds containing sulfur, and I don't have know much more about them. But what we know is that we work with a compound, which is the DMSP, which is contained in most of the photosynthetic microorganisms in the ocean. So microalgae, seaweeds, many of them contain this chemical compound. And in conditions of stress, then the cell, well, the release to the water of this chemical compound increases. And when it enters the water, it dissociates in two other compounds, DMS and acrylate. So we care about this because this compound, so the DMSP and its successors, DMS and acrylate, might be of interest for herbivore zooplankton who wants to feed on the algae and wants to find them in the water column. So, yeah, there's a theory that says that DMSCs enhance plankton predation. So this is a scheme from a paper that was published last year, which supports the idea that there's a positive feedback between this compound and a predation event. Because we have at the beginning, so that we have the microalgae, it emits DMS, they were working on DMS, it emits DSP, DMS, and acrylate. Predator senses it, finds the algae, eats it. Predation is a form of cellular stress, so the amount of this compound increases. There's a stronger chemical signal. This will attract more predators, and as usually algae don't go alone, maybe they go in a bloom. This will trigger a predation event. And yeah, something interesting about the chemotaxis to DMS is that it's supposed that actually this triggers a trophic cascade, meaning the herbivore zooplankton wants to eat the phytoplankton which produces DMS, so it does chemotaxis to it. But then we have the carnivore zooplankton who wants to eat the herbivore zooplankton. So it has learned that the herbivore goes where the DMS is. So he wants to eat the herbivore, but he does chemotaxis towards the algae. And this actually can travel up in the trophic chain, up to more complex organisms. So apparently they find that seabirds and turtles and penguins, so more complex organisms, also do chemotaxis towards the same compound, because maybe they want to eat some smaller organism who is doing, at his turn, chemotaxis toward this compound. And well, let's put a second fun fact about DMS, which is not about this job, is that the DMS, which is produced by the marine organism, is a lot. And from the water, there's a flow to the atmosphere. And this is actually then a precursor for sulfur-containing aerosols, which are cloud condensation nuclei, which can affect the global climate, because it can affect, on the big scale, the formation of clouds. But this was just a fun fact. Okay, so let's back to the micro scale. So all these stories that I told you about is actually not quite controversial, in the sense that there is no agreement in the scientific community if these compounds are chemoattractant for favoring zooplankton. So the zooplankton use this compound to find the algae, but there are also a set of papers or studies that supports exactly the opposite. So that it's a compound that the algae is producing to defend from predation. And for example, Nature Microbiology published in 2021 a paper belonging to a team and a paper belonging to the other team. So the experiment that they set up at the ICM is is framed between this controversy. So they want to they designed an experiment to see with 4 microherbivores that they have at the ICM what is the chemo response of these organisms towards these compounds. So the experiment is quite simple. It's a capillary assay, which is very typical in chemotaxis studies. So you have 2 capillaries. One is filled with a compound of your choice. In this case, they work with DMS, DMSP, DMS, and acrylate in 3 different concentrations. And then they have a second capillary, which is a control capillary, which is just full with water. And they offer the organism the choice between the 2 capillaries, and they see what if they like it or if they hate it and they go away from it. And what we did here at the Medea is the tracking of the trajectories of their videos. So they produced a lot of videos, hundreds of them. So of course it's a problem if you want to analyze them one by one. So we did the tracking, and now we have all the information about where the cells have been at each moment of the video. And now we try to get quantitative information out of the videos to understand the process. So the first question that we want to try to understand is so are they chemoattracted or not? So do they like the compound, or actually they go away from it? So what you see here are, well, for example, the results for 3 of the organisms for the maximum concentration of the MSP. And we can already see that different organisms will behave differently and will interact differently with the capillary. So, for example, there is clear chemo attraction for gyrodinium and carnodinium, but we see, for example, the gyrodinium just enters at the end, at the entrance of the capillary, but doesn't travel, while carnodinium seems well to like it and actually explore the capillary in the end. Oxyris is a mess. It seems to like the capillary by itself, probably because of the reflection, so there might be some phototaxis, like that it goes to the capillary because there's reflection. And we try to get some numbers out of it. So we can plot the distributions for each of the replicas in time of how many cells are in each of the capillary. And for each organism, we can try to get a scale, which tells us how much the organism entered inside the capillary. And well, this is important because it helps us to decide a scale at which we calculate chemo attraction. So I'm not going to calculate chemo attraction until the end for gyrodinium. I'm going to stay like in this length scale defined by the distribution. But for Keral, Tens, Raphael, Simon, it was more interesting than that because they linked this behavior to the use that each organism does of the compound. So from previous experiments, they know that gyrodinium is not consuming, that is not eating the compound. So they call it an explorative behavior, so it will follow the chemical compound to find the source that is producing it because it's interested in finding the source. While Oxyris, they found out that it actually eats up the compound. So it's chemoattracted by it, but it also consumes it and metabolizes it in its body. So maybe Oxyris is not interested in getting to the source of it because it can be interested in reaching an area where the concentration is high enough and then just stay there and it's around and when it's full, and he just leaves. But this is a theory. And then, well, we try to get a number for chemo attraction by, well, seeing as a ratio of the concentration in the capillary which is filled with the substrate and the capillary with water, and I will not enter in the details of the numbers. But we see quite some clear chemo attraction, at least of certain organisms towards DMS and DMSP, and we don't see a clear signal for acrylate, so maybe they don't like it, but they don't even go away from it like crazy. And then the second kind of question that we want to answer with the videos is if we see a change in the swimming behavior. So we quantified, okay, they like it or not. It seems they, on average, like it, at least for DMSP and DMS. But does this change something in the behavior, in the individual behavior of the organism? So the first thing that something that we noticed with gyrodinium is that the shape of the trajectory seems to change when the organism is going in, that are the particles in red, and when it's going out, that are the particles in blue. When the trajectory is going out are much straighter. So these are just some of the trajectories that I picked from the video. So we see that there seems to be a different behavior depending on the state of the organism. So if it has already traveled to the chemical source or if it's going away from it. And well, we are not through this kind of analysis, but it could be interesting because in general, the shape of the trajectory can tell us something about the foraging strategy of the organism. So in the micro world, it's always a trade-off between I want to eat, but I don't want to be eaten at the same time by something else. So for example, a very wandering motion is more effective if you are swimming between patches to find the source, but it also exposes you to more risk of getting eaten, while a very straight trajectory is a faster way to go away. So we see gyrodinium, it doesn't consume the compound, so maybe it gets there, it's understand after some time there's a capillary, okay, there's nothing here, let's go away as fast as we can, and I don't know, well, this, the shape of the trajectory might tell us something about the step of the foraging process in which the organism is. And so we want to try to get a very rough estimate of the straightness of the trajectory. So this is just the first thing that we tried, which is very simple. So if I want to go from a point A to a point B, I can take the path N, which is very convoluted, so it will be very long. with respect to the actual distance between the two points. So I can define my straightness parameter as a ratio between the two, and I will have 1 if the trajectory is totally straight, I go from A to B, or it will be, well, tending to 0 if I take an infinitely long path to go from A to B. And for example, if I run the distributions for gyrodinium at one concentration of DMSP, I start to see that there seems to be a statistical difference between the two sets. So the blue is going in, and if it's 1, there's a high peak, then yeah, there are much more straight trajectories in the particles going out than in the particles going in. So there seems to be a difference in the way the organism swims, depending on if it's entering or going out of the capillary. And this is the very last. So we also ask ourselves, are these speeding up or slowing down? So is the organism swimming faster or slower depending on its position in the chemical gradient? So if we take the distribution of the speeds as a function of the distance from the entrance of the capillary and the distribution of the modules of the speeds, we do see for gyrodinium, which is the same organism which has this change in the behavior of the trajectories, that the closer it gets to the source, the faster it swims. While, for example, if you take Oxyris, there is a very well-defined swimming velocities, which is independent on where it is in space. And that's pretty much it. So we see the light at the end of the tunnel. So we are about to finish this job, and it seems that we are joining the team of the progressing side. But let's see. And now the beer meter is full. We can go to the beer. And if you have any questions. I'm sure you have questions.
Sorry, I do actually have a question. About the differences in the trajectories going in and going out.
Mm-hmm.
I have two questions actually. So the first one is you showed trajectories that go into and out of the chemotractor capillary.
Yep.
Is there a similar difference in the other one?
Yeah, well, yes, I thought of this. Yes, there is. We don't see this behavior in the other capillary. Actually,
Wait, didn't say you do see or you don't see?
We don't see this difference.
Okay.
But actually, okay, I will answer your question better in the future because if I look for trajectories going in and out in the control capillary, it's so little that the statistic is not very good. So I'm finding trajectories going in as if it starts from a certain radius and gets close enough because I want long trajectories. So if I apply this filter to the control capillary, I get 3 trajectories.
Of course,
So, but this was on one video, so I will have to process, maybe putting them together. I have enough trajectories going in and out the control capillary so that I can have a statistic that we can call
statistic.
statistic.
Has any dependence on the concentration of
Yes.
the chemotractor?
Okay.
That was
problem. Yes, problem. I did this like 2 days ago, so I still didn't thought out loud about this. But so we have, of course, much better statistics for the case of maximum chemotraction. So if I do this kind of analysis for the DMSP 20, where I have the strongest, the stronger reaction, I get hundreds of trajectories, so my statistic is good. While for the other ones, the statistic is a bit worse. I saw this behavior, let's say this plot looks similar between the 3 repetition with the same compound and the same organism. So there is the same behavior at all the 3 concentrations. I cannot tell you if it's significantly different between replicas because I don't know, because I still didn't process the data well enough to see if the difference simply comes from the fact that in some cases I have less statistics because I have fewer trajectories, or if there is really a difference because I didn't put time in it yet.
Okay, my second question was...
There's already 2 questions.
No, but that was the second. That was the first 1B. Now the second question is if the if you're dinoflagellate or whatever is the...
Yeah, I think it's all dinos.
Okay. Chemotaxis to the source or whatever, to the capillary that has the chemotractant. Why do they go away then after?
Well, okay, so theories. On one side, for example, Oxyrhis. Oxyrhis is actually eating the compound. So it goes there, it feeds, it will have a maximum, a maximum amount of DMSP that it can metabolize. So I think that you're an organism, you went there, you ate, now you're full. The best thing you can do is to go away, because maybe your predator is also doing chemotaxis to the same compound. So I just want to go away from it.
Perfect. So wouldn't this then mean that you can have both a chemo attractiveness, or it can be positively chemoattractant or negatively, so you can have both behaviors, and therefore maybe that could be the reason why you have two camps, let's say.
In the studies. It could be. Sorry, what I remember from the papers that I read many months ago of the other side of the story, let's say, it seemed the kind of experiment that I remember was more that they were adding the chemical compound. For example, they were working with acrylate. They add acrylate to the system, and then they see a decrease in the successful predation events. But that could also be that they were masking the actual chemical trail inside the system, because you add chemical to it, and so the strength of the signal that the organism perceive is lower. So there's a set of studies that I think that the reason is that one. That there might be a chemo attraction or chemo repulsion depending on the state of the organism. It might be these experiments were done with the organism being starved. So they were very hungry. It could be that if you do the experiment with them that are with a very full belly, everything could change. Yeah, that could be.
I was actually going to ask about this, because it seems you are arguing that it's going fast on a strike because I guess it's not hungry anymore.
Yeah.
So it would be very cool to try the experiment with this whatever it is, this
Gyrodinium.
That has eaten a lot, a little, and nothing.
Yeah. Actually, the fact is that I think
can you manage to get them to eat a little bit? Is that possible?
This is the biology question. I don't know. And actually, my biologist is now on an internship in Australia and do not answer to me. So actually, she doesn't know about this. But yeah, I mean, I would think something. I mean, okay, if the theory is right, and then my theory, which is totally random and comes from someone that has no background about this, then yeah, I mean, I would expect to see a different behavior depending if they want to look for food or not. But really, this is like what I thought about when I saw this behavior, but I didn't talk about it with anybody who has actually the background to discuss it. But
some people study how much they eat depending on how much food there is in the water, I guess. You know, if there are some groups working on how much this eat depending on the kind of water they have.
No. Okay, I have no idea, really.
That's very cool. That's very cool. I was also going to ask what was the reason to thinking that this is anti-grazing?
Anti-grazing?
Yeah, you know, the opposite. You said there were two opposite theories about this, but you did not explain much the opposite one.
Yeah, because I'm on the one side.
So I guess there is a basis on it.
Okay, so the studies I remember, for example, maybe, wait, let's go back. So from what I remember, so we are here. So with DMSP, it produces two compounds. Apparently, there are some studies that says that actually the harmful one is the acrylate. So that there can be some species which actually don't, that it's harmful to them in some way that I don't remember. So, for example, they did experiments and So DMS, if I remember correctly, DMSP actually dissociate in the water, not because of the water, but because when the cell breaks, so cellular stress, I think it's a way to say that the cells is breaking down because or it's too hot, or it's because it's being predated, etc. So when the cells breaks down a bit, it also releases an enzyme, which is the DMSP lysis, which is the one that then in water they meet and they separate. So for example, they made a study in which they would take a genetically modified organism which do not have this enzyme, and saw that the predators predated more on the ones that didn't have this enzyme. So the ones that when it's in water, they don't, so this chemical reaction do not happen, and so there is no acrylate. So it might be a trade-off between I want to use this chemical compound to find my food, but this other compound is harming me. So if I can avoid it, I will avoid it. But if there is the only food I have, well, I will follow the DMSP and find the food. And also, I mean, biology is horrible. Like there is so much variability. So, for example, if I go here, okay, so Stromodinio is an organism that say nothing to me, and it's not chemo-attracting at all. So, if the index is 1, there is no difference between control and substrate. So maybe you do the experiment with this, and okay, this one likes it a lot, but then, I mean, there are thousands of organisms, thousands of species, thousands of things. So infinite possibilities. So maybe this theory can be true or not true, depending on the species,
on the organism,
depending on the environmental conditions,
and also the communities of organisms also interact between them, and then the result can be different as well.
Terrible.
Very nice.
I just have a doubt about the way you make the statistics.
Yes.
Because the time is out of your
In which
calculation.
statistics?
The one on the relation between distance and length.
Wait, because maybe there is, sorry, which, like the part of the chemo attraction or the trajectory shape?
The trajectory.
Okay, here I am more on, yeah. So what is the...
If you look at this movie,
Yeah.
you see that even the red trajectory had the tendency to have chunks of
The drift.
that are
No.
straight lines and changing direction quite a bit. It looks like the natural way they move is through a sort of a devil flight or something like that, going in a straight line for a while and then changing direction. Now, it may happen that you see all these trajectories, but in the point where they are feeding, you spend a lot of time going around, so that will give you on the distribution, they will populate the left part of your distribution.
Sorry,
If you stay
it's to stay a lot.
Time,
Yeah.
Wandering
Yeah,
around the source of food because you're really busy. That will compute in the distribution
I understand.
as a lot of
Okay, here I can defend myself, which is, so usually when it comes here, I lose track of the organism, because either it interacts with this black line of the capillary, or the density of organisms is so high that the tracking software cannot track anymore. So usually I don't have any trajectory in which I know the dynamics here. It comes to this area, and when it comes to that area, I lose the track. So I mean, I don't know if this answer, but I think that it's most of my trajectories is not like of going around this point, because it always break there. But I don't know if this partially.
One should look carefully.
One should look carefully. And as I said, I mean, I started this kind of analysis at the beginning of last week, so I still have to put time in it and to refine it. Yeah. Yes.
Me?
Yes.
Actually, just one mathematical question. Like, it seems that these trajectories, the blue ones, are quite straight.
Yes.
But the ratios that you calculated were all below 0.2. What means that the path should be 5 times longer than the direct shortest path. If you go to your distribution, there, the PDF is the ratio between D and L, right?
The PDF? No, wait. This is the ratio between P. Is the ratio between.
So no, then it was close to 1.
No, this is where the normalized, where it's normalized to the counts and to the width of the of the bin, so that the sum
sorry,
if you
I
integrate
just
is 1.
misunderstood your graph. Sorry.
Yeah, no, but yeah, then you see the peak is around 0.6, so it would be that it's more or less half.
Yeah.
So the shortest path is half.
Okay, but the going out path is very straight. Yeah. So it's correct. And then one question: do they have a sense of orientation, or they only follow gradients?
Right. This is a question I don't know how to answer. No, I have no idea. Like I don't really work with these organisms apart from tracking the trajectories. But okay, like I guess it depends on what you define orientation. Like we talk about very simple organisms. So in general, maybe they have a few receptors, maybe one for light, one for a chemical compound.
Yeah.
So what orientation means.
But none for gravity, for example.
There is, okay,
Sorry.
it's a world of possibilities. I think that now I can pass this to Idan. But there is also it's the gyrotaxis, no? No.
You can do gravitaxis, yeah.
Gravitax, like there is also organisms who who can sense gravity and, they react to. There is people, there are organisms that are doing magnetotaxis with the Earth magnetic, I don't have the word, field, thank you. So, yeah, it's a world of possibilities. There are species that that orient through gravity, or that you can orient through the magnetic field. So, yeah.
But at least it knows how to go straight, also, if it wants.
Apparently, yes.
Or does it sense the gradient again? Because the gradient might be also like around the capillary.
Okay. I would think that they go straight. I mean, in this case, the direction going straight implies also going in direction of maximum gradient. Because I didn't show it, but we did some experiment with with a dye, where the shape of the concentration gradient around the tip of the capillary is pretty radial. So going radial coincides in this case kind of with the direction of maximum gradient. So they might be going in this direction, straight in this direction, meaning going straight in the direction of the maximum decrease of concentration. I don't know, is that answering the question? Yeah.
Yes.
Yes.
And how do you track every individual?
So there's a magic. No, so it's a Python package. It's very well done. It's called TrackPy, and it's very user friendly. So you can import a video, and then you have to do some background extraction, increase enhance the contrast in the image, etc. And then you prepare it, and then he takes frame by frame all the circular spots. So because in the end this is a very easy to track shape, because it's a circle essentially. So it tracks the position of the circles, and then it have inside some routines that, based on some probability calculation, will find which is the most probable cell between two consequent frames to be the same cell. I said it wrong. But okay, so let's say this cell is going here, so it detects that it's here, and it knows from the previous frame that it was going in this direction. So it calculates for the next frame in which will also this point maybe moved here. It can connect. It can understand that it was this point going here from here to here, because in the previous frame it was traveling in a certain way. So I think it has a range of probability to assign which cell is which cell in the following frame. And then if there are too many possibilities that this cell might be this one, but also this one, because, for example, the density is very high, then it just breaks the trajectory and tells you, well, I'm sorry, I cannot do it. And that's why I think I lose them there, because the concentration, like here, the concentration becomes super high, and so it cannot really assign from a frame to the next which cells correspond to what cell. But it does it automatically, so you don't have to really do anything.
Thank you.
You know, pollinators, we work with pollinators and they do this. When they are searching for food, they are going like this. And when they are full of food, they just go away very fast and far.
But because I also guess it's the same, no? Because if I'm searching for the flower or whatever, so I have to search. But once I have my carriage,
they could stay. But they don't.
But why should they stay if they already fulfilled
it's not a matter of predators, I think. In the case of pollinators, because I don't know why they go away, but they do.
Okay, yeah, that's interesting.
Yeah.
You say that the gyrodinium eats the DMSC or just looks for the algae?
No, gyrodinium doesn't consume the compound. They did experiment with with a dye which was radioactive, I think. And then they checked if afterwards the cell was also radioactive. So if it was radioactive, it's because it was consuming the compound, and they found that gyrodinium do not.
So this could also be another search strategy. That they explore this area, they see that there is this chemical signal, but there is no food here.
Exactly. That's what I think.
Let's search for another patch. But to search another patch, you have to get far from this.
Exactly. To have a long, if it was a Levi flight, a very long run, to go to another point and start. Yeah, that's the hypothesis I would have, but really I didn't talk about this with anybody. So. Yeah, it's my guess, but it might be wrong.
But you have super nice trajectories.
Yeah.
I wonder if you are also applying. There are a lot of methods that are using animal movement that you can segment the trajectories, like searching for behavior. And consider it's a kind of multiparametric analysis. You calculate different estimates for segments, so then you can see so here they are. It's a more area-restricted search, it's a Levi flight, so you can quite easily classify the different behaviors. Or even if you know the real gradient, the DMSCs. Do you know the gradient that you have there?
Yeah, that's the trickiest question, which is the real answer is no, because the experiments. In the experiment, the dye is not fluorescent. You cannot really know how the real field is, and you see it in the videos that you have a lot of convection and it's not static. There is crazy drifts at certain moments, etc. What we try to do now, posteriorly, is that we fill the capillary with a dye, and now we filmed it, and now we want to reconstruct the evolution of the gradient with this geometry. More or less in the conditions in which the experiment was done, but this will give us an order of magnitude of how the gradients look like in the experiment. And also there is a lot of variability just by doing the experiment of the dye that I did here. You're talking about something which is super small, you're holding it with the micropipette, so you put it down and then you move it a bit because it's not in the position where the camera is recording. I'm feeling that between here and here it's 0.5 millimeter. So, and if you do it manually, it's a mess. So when I was doing it with the dye, I had to do 20 repetitions to get one in which the gradient was radial and nice and circular. When Peralta did the experiments, she didn't have the dye, so she will have put it as best as she can, but for sure, who knows in each video how the gradient looked like, which is also why it was so difficult to analyze these videos, because there is so much variability between the variability due to that it's a biological system that it does whatever it wants, and then if your repetition every time changes a bit, it's a mess to find a way to actually analyze the videos in a way that you find an analysis that you can trust. I don't know. Yeah, that's everything I have to say about it. To the beer? Ah, ya, es que se me olvidó decirlo.
No, mejor así.
Sí, sí.
Ah, espera. No.
Ah, ya, ya.